This is lab number 3 for Colby's instrumental analysis class, and it's an IR Raman evaluation of ethanol vodka in vodka by me, Kristen Esdale. So to get started, we wanted to see if we could experimentally calculate the ethanol content in vodka. So the brand that we used was 5 o'clock vodka. Its reported ethanol content was 40%, which corresponds to 80 proof, and it was bottled by Laird and Company in Scobeyville, New Jersey. And a picture of it is shown on the screen at the right. So to do this experiment, we needed to make samples and standards. So for the IR, we added 25 mils of vodka to a falcon tube. We had 5 of them. And we either filled them with 1, 2, 3, 4, or 5 mils of pure ethanol, 100%, 200 proof. And then we would fill the rest of the sample to 50 mils using our milliQ water from our filtration system. For Raman, we knew that we needed to have higher concentrations of ethanol, so we added 25 mils of vodka to the falcon tubes like we did before. And then we added either 10, 15, 20, or 25 mils of ethanol, and then we filled the rest of the sample with 50 mils of milliQ water. For Raman, we also used the previous 5 that we had made up for IR. We just wanted to have higher concentrations so that way we would get better data. Here's a picture of our IR spectra. We have 4 main peaks, one here at like 1275, one here at 1095, here's one at about 1050, and here's one at about 875. You can see that there are different lines on the graph, so it looks like there's about 5 or 6 lines. Those are for each one of our standards, so as the concentration of ethanol went up, then so did the peak intensity. Here's the results for our IR. The first column is the flask number. The second column is more important. It has the volume of the standard that we had. In the third column, we have the standard concentrations in solution, so that means that's our ethanol concentration in each sample. In the fifth column and seventh column, we have peak height and peak integral. So when we did IR, what we did was we used 2 different methods to see which one would give us better data. The peak height corresponds to the peak intensity and just the raw height of that, whereas the peak integral method involved us taking the integral over the entirety of the peak. So we did it both ways to see which one would work better. And this is how we calculated ethanol for IR. So we have peak integral on the y-axis, and we have the concentration of ethanol on the x-axis. We got a slope of 6.3 with an intercept of 16.2, and our r-squared of 0.99902, which is really good. The second graph, the one that's in the bottom right, is the peak height versus the standard of, or the amount of ethanol. We had a slope of 0.1317 and an intercept of 0.5523 and an r-squared of 0.992. So not as good, but still pretty good. So here are the results and stats, just a summary of our IR data. The wave numbers that we used to calculate ethanol were 1050 and 1095. I think we ended up using the 1095 data more heavily. The calculated ethanol concentration using the peak height method was 45.39 plus or minus 0.9%, so not quite within the realm of our literature value of 40%, but kind of close. And using the peak integral method, we got 29.9% plus or minus 0.32%, also not within the range of our literature of 40%. So the peak integral method was definitely worse than the peak height method, however. So here are the results from our Raman data. We had 10 samples that we ran. The second column has the volume of the standard, so we had a blank of 0. We used the 5 samples from the IR, and then we had 4 more just with higher concentrations. Third column is what the standard concentrations in solution were. And in the last column, we have the counts, which is the intensity of the peak. And so this is the graph that we use to calculate ethanol in using the Raman data. So on the x-axis, we have the concentration, and on the y-axis, we have the counts. And so our slope is 0.4467, and our intercept is 36.938. Our r-squared is not great, it's 0.72, but we carried through the calculations using these data. So here's just a summary of the results and stats from Raman. We only used one wave number, which was 882.53 inverse centimeters, and our calculated ethanol concentration was 82 plus or minus 21%, which is not very good. We have high error, and we're nowhere near the literature value of 40%, even including errors. So here's a comparative analysis of the instrumentation. IR was much more accurate and much more precise. We used, for IR, we had wave numbers ranging from 800 to 1400, and for Raman we had 500 to 1100. So we had the same number of wave numbers within each method, but it just happened that they were, shifted by a little bit. So in terms of time per sample, they were both very quick. IR was a little bit faster, but for Raman it only took 30 seconds for us to get 3 data points. So they were both very fast. IR required more technical expertise, I would say, because the software, the instrument was more high-tech, whereas the Raman was not nearly as technologically complex. However, it took a little bit of getting used to because there wasn't a mouse. And also for Raman, we had to be very careful with regard to bumping or touching the instrument. Otherwise, we'd have to set everything back up manually. Whereas with the IR, it was all enclosed and all of it was computerized. So it's really hard to compare which one is the better instrument, because one of them is 25 years old and the other one is less than a year old. So it's very difficult to make a comparison, and I think in order to make a better one, we would need to run more experiments, to be honest. But in this case, IR was definitely the winner. So IR and Raman are both based on vibrations of molecules and how bonds between atoms either stretch or bend or rotate about or twist about a plane, so that way the dipole moment changes and our spectra can be created, essentially. So in order to figure out which vibrations corresponded to the peaks we had, we did normal mode calculations using WebMo. So in the first column, we have just the raw data that WebMo spit out for us. Ethanol has 21 normal modes, so these are all of them that WebMo found. The second column is corrected theoretical values. So in order to correct for the Hartree-Fock method, we needed to multiply all of our vibrations by 0.9. And so the corrected theoretical shows that adjustment. The third and fourth columns mark whether a shift or a vibration mode was IR active or Raman active, or both. So IR active peaks included 868.998, 1035, 1075, and 1260, and those are the ones that we observed. For Raman, since we only used the one peak, we used literature values to find out what the expected Ramans would be, and those peaks were at 407, 868, 1035, 1075, 1260, and 1470. And the actual expected Raman values were 430, 882.53, which is the one that we observed, 1055, which is again literature, 1090, 1280, and 1460. So we're getting pretty good correlation between our expected and our corrected theoretical calculations from WebMo. And for IR, we observed peaks at 875, 1050, 1095, and 1265, which also correlate pretty well with the corrected theoretical data from WebMo. And we can also see that there are some peaks that are both IR and Raman active, and then there are 2 peaks that are just Raman active, which is really interesting. The other thing that we wanted to see is, with what we saw, what modes were causing those peaks to happen. So if we had explored the full spectrum of the Raman, we would have had an OCC bend at 430. We would have had an OCC stretch at 882, which is what we actually based our data on. We would have had wags at 1055 and 1090, a twist at 1280, and a methyl bend at 1460. Whereas in the observed IR that we have the OCC stretch, the 2 wags, and the twist that are causing those peaks to occur. And so these are plots of theoretical frequencies versus observed or expected frequencies. So the one in the top left over here is for our IR. On the x-axis we have observed frequencies, on the y we have theoretical frequencies. We have a y of 1.00, an intercept of 13.759, and an r-squared of 0.998, which is really good, showing that there's very good correlation between between the theoretical and the observed. For Raman, we did the same thing, graphed observed on the x, theoretical on the y. We had a slope of 1.0094, an intercept of 25.636, and an r-squared of 0.99988. And just to give credit where credit is due, we found the expected Raman values at www.sacredlaser.com. This link was live on 4/17/15, so it was there with peaks and literature values for ethanol in Raman, and that's the lab.